Welcome to this video where I'm going to go through higher level topic 9.2 on Diploma of Program Physics, namely single slit diffraction. Basically, if if the wavelength of the light is the same size or smaller than the slit itself, then we're going to get diffraction. And because we can imagine diffraction occurring both from the center of the slit and the edge of the slit, then we get an interference pattern on the screen with a large central maximum and then a minima either side, and then another maxima. Now, the condition for destructive interference is that at this point P we have a half a wavelength path difference in order for there to be destructive interference. So if we make the distance between the slits and the screen very large, then these lines can be considered to be parallel, and this distance here between B and this point here is equal to the path difference, which is lambda over 2. This distance between AB is half of the slit width, if we assume that B is exactly in the middle. And from geometry, right angle geometry, sine theta is lambda divided by 2 divided by B divided by 2. The 2's cancel to give us that sine theta equals lambda divided by B. Now, if we assume that theta is very small, if we measure it in radians, which is important to do, then tan theta is approximately equal to sine theta, which is approximately equal to theta. That's what we call the small angle approximation. So therefore, we can simplify this. Sine theta simplifies to theta equals lambda divided by B, and this is in fact the formula given in the data booklet. But we can also work out theta simply by measuring the width of the from the central maximum to this first diffraction minimum, and dividing that by the distance between the slit and the screen. Most commonly, though, in experiment, we measure the width, the angular width, which is the distance from one minimum on one side of the central maximum to the minimum on the other side of the maximum. So that will be 2 lots of y. The consequences are therefore that if we have a larger wavelength, we're going to have a larger diffraction angle, and if we have a larger slit width, we're going to have a smaller diffraction angle. So therefore, if we had blue light instead of red light, the diffraction pattern would look like this. It would be more bunched together towards the central minimum. You also have to know that this, if we're plotting intensity against diffraction angle here, that the ratio of the primary maximum to the first secondary maximum is, this one is going to be 4.5% as big as this one, and that will go for the one on this side as well.